Okay, so we'll start now. Can anybody confirm if my voice is audible and the screen has been shared? Okay, so I guess that is yes for both. So we'll start now. Okay, so we are here. So we'll finish the two-dimensional simulation today. The last class we discussed PML, and today we'll discuss the plane wave impinging on a dielectric surface. Yeah, so I hope everybody recalls the formulation for FDTD in two dimensions. We'll do a brief recap of what we did in the last class in PML and take any questions you might have. Yeah, this topic PML is a bit more complex as compared to the other topics that we have covered till now. And once we have discussed PML uh, from yesterday's class, then we'll start with what we call as total field and scattered field formulation, and an example in which a plane wave impinging on a electric cylinder that we will see. So we'll start with today's recap. So yeah, the last class we saw that for a wave traveling in FDTD, we need boundary conditions, and to do that, one of the best ways is PML. And for implementation of PML, we we try to match the impedance from the problem space to the PML region, and then in the PML region, we make the PML region as lossy so that the wave decays uh, in the in the PML region. So how do we do that? So for example, if the a wave is traveling from medium A to medium B, its reflection, the amount of reflection is given by this expression. And over here, the eta is the interesting impedance of the medium A and B. So the impedance is calculated depending upon from the uh, permittivity and permeability. And up till now, what we were assuming that the permeability remains constant for both the media, and what then the permittivity changes when when we go from one medium to the other. So so for PML, it really does not have any physical meaning, but what we do is we vary the permeability along with the permittivity such that this particular ratio remains constant, and if this ratio remains constant, the eta also remains same. So what will happen is you move from one medium, from medium A to medium B, such that the impedance of both the regions uh, are same. But what is happening is the both mu and epsilon are changing. So so we will not see any reflection if gamma remains same, and for gamma remains same. For gamma to remain same, this if the so what we do is we make the impedances for both region A and B equal. And but up till now, what happens if there is even if there is no reflection, it does not solve our problem, because what we want is the wave to decay in the second region. And for that, what we do is we make both mu and epsilon, the permittivity and permeability, as complex. So the for the imaginary part, if both of them are complex, the imaginary part represents the decay and like the losses. So the imaginary part will cause it to decay. So this was the logic behind the PML. And so for starting with the formulation of PML, what we do is, since we are introducing the imaginary part, we'll again move from the time domain expressions to the frequency domain expression. So we will replace the d by dt by uh, j omega, and then we will and similarly, so epsilon over here can now be easily replaced by the complex part. So we move from the time domain expression to the frequency domain expression, and then we introduce these fictitious epsilon and mu values, and so these particular epsilon and mu values, they remain one in the problem space, and their effect comes into play when we move to the PML region. So they do not have any actual meaning. We are just introducing them such that they will cause the wave to decay in the PML region. So once we have and we like we have introduced two values for each epsilon. So one will affect the decay in the x direction, and the other will affect the decay in the y direction. So we have introduced epsilon x and y and mu x and y in these expressions. And once after introducing this, we will we will perform the we have to calculate the values for we have already introduced these arbitrary values, but we need to know what should be their expression such that it causes the decay. Now for that, Sachs has given two laws. So according to Sachs, to successfully implement PML, what we need is that the problem space, or if, for example, if since in this case the problem space is vacuum or free space, its impedance should be equal to the impedance of the PML region. And over here, this is one because we are taking normalized units. So basically, this is saying that there should be no reflection from the problem space to the PML region. And in the second case, it has given a relation between the uh, this epsilon, fictitious epsilon and mu values that we are introducing, and it says that the variation of epsilon in the x direction should be inverse of the epsilon in the y direction. So based upon these two, we are assuming that the permittivity and permeability, these fictitious values are of this particular form. So this is very standard form of the permittivity and permeability. And over there, we need to find out the values of EFM and sigma DFM. And for that, based on these two criteria, to satisfy them, we choose epsilon fm and mu fm as one, and we take this relationship between sigma dm and sigma hm and sigma d. So we once if we choose this particular set of values, it satisfies the both these laws. So choosing these values, we are satisfying these laws. And if we substitute these particular values and try to calculate the uh, eta m, we see that we are achieving that this ratio is equal to 1, which is equal to eta naught. So we have satisfied the first law, we have satisfied the second law, and now the only variable that is left with us is sigma x. And we can you and now this we can define a particular sigma x as sigma represents loss, and and we will define it such that the wave, as soon as it enters the PML, it will not have any reflection, and based on this sigma, this the wave will decay. So we had this set of Maxwell's equation earlier, and after introducing the values for the expressions for the fictitious mu and epsilon based upon the laws from Sachs, we have this set of equation over here we are just considering the PML in x direction. So for simplicity, we are just skipping the PML in y direction, and once we are done with x, we'll use the same ideas to introduce the expression for y as well. So So we'll start with each expression one by one and see do the finite difference approximation to get the update equation. So we have already covered in the last class, but I think I'll go over them one by one again. And the second part of this lecture will be start the new topic, which is the TFSF. Okay, is it 1 plus sigma x in the combined form or separate in the numerator in the previous slide? Let me check. So yeah, so this is 1 plus sigma. Okay, I think yeah, there might be this. This should there might there's an error, I believe. Yeah, so this should be 1 plus sigma by j omega epsilon naught. Yeah, there's a typo over here. But anyways, this will
Uh,
result to numerator
I think
equals 1.
Anand, there should be sigma dx. I think if you see the
Yeah,
expression in the one
yeah,
plus
yeah, yeah,
sigma
yeah,
d.
yeah. So yeah, apologies. Yeah, took these expressions from the textbook, so very sorry. Yeah, this should be this will be sigma d x, and this 1 plus the numerator denominator thing should be there. But anyways, this will result in the expression to evaluate to 1, which is what we are uh, like required for us. So we are just showing that eta naught will be equal to eta m. So hence there should be no reflection as we move from the free space to the PML region. But yeah, so you can correct this. I'll try to modify this before sending the slides. Yeah, thanks for pointing out. Thanks, Priyank. Thanks, Ankit. Yeah. So we have this particular set of Maxwell's equations, and for each expression we'll go one by one. So taking the first expression, we again we know that j omega represents a derivative d by dt. So we use that to get the time derivative of the first x for dz, and for the second term, this dz can be represented as an average of the dz values at the two time instants, the previous and the new time instant, and we can just take the coefficients common, and this is what this so this expression is for the left hand side. And for the right hand side, again, these are derivatives in space. So this is pretty standard that we have already evaluated in the previous for the 2D case. So we already have the expression for the left hand side, and the right hand side is known to us. So we'll just put these values, and this gi1, this gi2 and gi3 are basically the coefficients which will evaluate to this. So you can like if you want to, you can verify by doing it by your own. So this is the update equation that you will get for the first expression. Now moving to the so before we go to the second expression, we'll first do evaluate the third expression. So the third expression is very similar to the first expression, where we evaluate the left hand side first, and so this j omega multiplied by hy is basically the time derivative. So we already know how to take the central difference for time derivative, and this j omega will multiply with this denominator and will just have hy, and for hy we'll again use the average values at two time instants. And on the right hand side we have a spatial derivative which will like which is also known to us. So using that, we evaluate and we get this expression. And this f2 and f3 will this coefficients you will get. So the first and third expressions are pretty straightforward, which that we already know. In the second expression, what we have is this negative power. So for this negative power, we'll take this particular term and multiply it on the right hand side. So after multiplying it on the right hand side, so we will have one term as dy. This is a spatial derivative, and over here we have a spatial derivative and a j omega term. So to evaluate this, what we do is first we take this particular term and we do this central difference scheme over here, and we just give this particular term as use will we rename this as this curl x by del x, so that we don't have to write this entire thing again and again. Now for the left hand side, we use the this time derivative expression, and we have so this is pretty straightforward. From this hx can be obtained from here to this expression. Now for the right hand side, uh, this particular term can be represented by curl of x, and this particular term is now basically, so we know that 1 upon j omega is integration in time. So for integration, uh, we we have introduced this summation term, and so this particular term remains same, this epsilon naught, this 1 upon j omega becomes the integration term, and the term inside the integration is dEz by dy. So that is again represented by this curl x by del x term. So for this expression, this becomes a bit complex, but yeah, so this is what you will achieve for the second expression. Now then again, rearranging it so that we get the latest value for the hx on the left hand side and all the other things on the right hand side. So we get this expression, and you can then again we like this is the update equation for hx, and for this you will need to calculate this curl of x, and this we have replaced the summation term by this this term I, which is essentially keeping track of this integration part. So I adds the curl of e value to itself, so that we have just one variable over here, and this hx is then calculated in terms of the previous hx value, the curl of e, this particular coefficient, and I, which has its own update equation, and curl of e is calculated using this expression. So this is these three expressions is actually required for the second Maxwell's equation.
Anand,
So we have so yes.
have a very small problem. Look at the del Ez del y. Is that del x in the nominator or del y should be?
Okay, so the previous class we discussed that for simplicity we are assuming that the FDTD space has square grids, and hence del x will be equal to del y. So and instead of using del x and del y both, we will just use del x for the entire like formulation.
Okay, thank you.
So del x is equal to del y, and to avoid having too many variables, we are using del x. Ankit, was that clear?
Yeah, thank you. Thank you.
Okay. Sigma di or sigma dx? That means. Hmm. Okay. Yeah. So this is just choice of variable. So in this update equation x, but like this particular I over here is representing the basically what is changing in the x direction. So once we switched from these analog expressions for Maxwell's equation to these discrete update equations. So I basically translates to the one as we are moving forward in the x direction. So I will refer to the nodes in the x direction, and j will refer to the nodes in y direction. So we are looking at the variation of sigma in the x direction. So we are using sigma this I. Now, Priyank, is that clear? Yeah. Yeah, so this sigma is so right now we are looking at the variation like the PML in x direction only. So and for PML in x direction, we want to decay the wave what is traveling, which is hitting the x boundary, and so we need to vary the conductivity, which represents the loss in the x direction, and hence this is sigma dx, and So over here, that is why we are and I is basically I is used for locating the nodes on the in the x direction. So that is why we have I over here. So all this we covered in the last class, but again, like last class was very overwhelming, I believe. So we are going through this, and you can uh, try to use a pen paper and go write the update equations yourself. This will become more clear. So we have already seen like the PML implementation for this set of equations, which was just meant for the x direction, and like but since we are working in 2D, we have to apply PML in the y direction as well. And for y direction, these terms will again appear in the Maxwell's equation. So these are the final Maxwell's equations which we are concerned, and we have to formulate the PML for this expression. But we have already seen how to do it for these terms, and using the same mathematics that we went through, we will find out the expressions directly. So I'll discuss them briefly, and you can try to do all the steps by yourself. So just one thing that we have to notice is that over here the second expression had this minus one term, but over here the third expression over here is having the minus one term. So the treatment that was used in the second expression over here will be used. The same treatment will be done to the third expression, and the second expression will be solved like the third expression over here. So the only thing that new which happened in the PML was this particular term, and the how we got this term over here, like how to represent the fictitious epsilon and mu values. So for x direction, we had this three set of equations, and for the y, we have this set of equations. And if for the first expression, we have just included this particular term over here, and hence for that you will uh, obtain this set of math. Like this is will be the update equation. So a few more variables are introduced, and instead of so you can try it on your own. This is what you will get. So there's nothing much to worry about in this, and especially given this particular first expression is very simple. In the second For the second expression, we saw that we already had this I over here and curly over here, and okay, so for the third expression, okay, sorry. So this for the third expression, we over here we just had this simple update equation, but since we have introduced this term over here where we this there is this minus one thing going on. So this will go towards the right hand side, and then after that we will again do the like finite difference scheme. And so and once you have done all that, you will see that you will use this curl of e. For the first expression, there is no inverse expression. Yeah. So in the first expression, there will be no inverse expression, and yes. So in the first one, there is no inverse expression. Let me see why was that. Good question. Why did I not notice this? Okay. So the first expression, what is happening is, yeah, the Sachs law is valid for both epsilon and nu. And yeah, for the question that the first expression there is no inverse expression. This is happening because the dz is you the for the dz the epsilon has to be varied in the z direction, and this epsilon f this so the inverse expression is actually dependent on the this if you notice this particular coefficient of this term. So this is happening for the z direction, and in the z direction there is no like we the dz is only the epsilon is only we are worried about in the z direction. But in for hx and hy, what we're having is this: we have this fx and fy, and for f and when we do it for the y direction, this will become fy and fx, and that for that reason. So the epsilon over here is varying. This coefficient is for the fz, due to which we do not have the inverse term over happening over here. Yeah, like, was that clear? Yeah, so this fx and fy are inverse, and similarly, but like, since there the dz is being updated in the z direction, and we do not have anything traveling in the and for the dz we do not have any thing like any other wave traveling in the x or z direction, x or y direction for the for fz. So we do not have any inverse term happening in the first expression. So we'll quickly move towards. So we were here. So the third expression, since there is this inverse term over here, for that we have if you will follow the steps that we did for this expression, the second expression for the PML in x direction, no, you will end up with this curl of E expression, which is same. And there's this I term which will keep track of the integration happening due to this 1 upon j expression coming in the right hand side. And the final hy will be updated using these three coefficients and the previous value of hy, the curl of E, and the integration term. And similarly, for the second expression, we already had this curl of E, I, and hx term over here. The only thing which got added was this particular expression, and so this will not bother you if you try to solve it. So this will, yeah, so you will end up with this again, this expression over here. So till now we have yeah, so we have seen the update equations for the in the PML region. Uh, for the three for dz, hx, and hy. And what happens is we you don't need to actually we keep like proper values for sigma that should be compliant with what is available in the nature. So since we are focused with simulations over here, instead of substituting the sigma values over here, you can replace the entire thing. You can replace the entire this expression, which will appear in all these coefficients by a term xn, and you can just put values of for xn such that the wave decays in the PML region. So what we do is in all the expressions that for f1 to fi1, fj1, all these things, this will all have this particular expression, and we replace that by xn. So the final expressions that you will see for the coefficients will look something like this. This fi1 will become xn, gi2 will become 1 by 1 plus xn. So once you have all the coefficients looking like this, you have to only worry about the xn, and we define xn by using this expression where this particular this 0.33 value and this power has been found out empirically that this works best for the PML case. So using this expression you find out the value of xn, and using the xn you find out the value of coefficients, and use these coefficients in the update expressions that we have already got. So we have all, so we had the update equations where we had these coefficients, and for these coefficients we have find out how to substitute their values. So till till Sachs we had this sigma as the only thing that was unknown to us, and we have defined that as well. So using all these formulations, we are ready to write the code for PML. And then last class we also had seen the code. So the major changes which happened was you need to calculate. Let me use pen. Okay, so major changes which happened was you need to calculate this, initialize the PML parameters. So the thing was like that, and that the PML inside the PML region, this the coefficients did not bother the update equation, such that this gi2 remained 1 in the entire space, gi3 remained 1 in the entire space, and if I1 remained 0 in the entire space, uh, and this goes on, like these expressions remain either 1 or 0 in the problem space, and inside the PML region they will assume values. So for the PML region, we update the gi1 gi3 uh, like this. So what we do is we calculate, we define this and this number, the length of the PML. Okay, so one thing that I missed, that is we usually take the PML as 10, the number of nodes in PML as 10% of the total problem space. 10% of the, so for example, if you are taking 100 nodes over here, make sure you have at least 10 PML cells so in this direction and 10 PML cells in this direction. Yeah. So we calculate this x num and this xd, and based on, so this expression is nothing but what you already saw, this 0.33 into this term, right? Whatever. So so, so this thing is being calculated over here, and you assign this 1 plus xn, 1 minus xn, this all this. So this is what we saw in the previous slide. So so we calculate the coefficient values for this. This is for the x direction. So this is all for the x direction, and similarly for the y direction, we and this is for the y direction. So similarly, you calculate the cube term xn over here, and then assign the PML value. So this j thing is basically working for the PML in the left hand side, like if y is varying in this direction. So you have a PML over here, and then again, as soon as the boundary ends, you have a PML over here. So this j2 and j minus j, this thing is working over here, and this thing is working over here. So yeah, you need to make sure that you have applied PML in at both the edges. Similarly, for the x also, you must know that you have applied PML over here and PML over here. So so before starting the main part of the code, you have to make sure that your uh, region has all the coefficients either 1 or 0 in this region, and has the correct values for the coefficient in the PML region. So till here you have already you have defined the PML boundary, and now as so you define the source, you define the plot window, and you start with the main part of the code, and whatever the update expressions that we have calculated for the dx. So we saw that we have included this these coefficients. This particular update equation is used instead of the previous one. So what happens is this particular expression becomes equal to the simple update equation that we had seen earlier, because this gi3 this term will become 1 in the problem space, and if this becomes 1, so this will result in dz equals dz plus coefficient times h minus h, something like that. So, and for in the case of PML, this particular coefficients will come to work, and they will decay the wave in this region. Similarly, so over here you calculate the Ez from dz. So this expression is same as before. No, and for hx and hy, we had seen this. We needed 3 expressions. We need to calculate the curl of E, the integration, the term which kept track of the integration, and this update expression for hx and hy. So yeah, we have seen how we got here, and this is all for the plot window. And so this particular, uh, this is all that we need to do for PML. So if you have any doubts, we will take that. We can discuss now regarding PML and anything from 2D. And after once, and after this, we will start with the total field and scattered field formulation. I might have rushed over here, so if we have time, we can take questions. Okay. I I guess there are no questions. Even like if you can go through like the material once again, you should refer to the textbook by DM Sullivan. So all these codes and formulations are from this book, and yeah, whatever doubts you might have after going through the book, you it will be answered from the text itself. And if you have any doubts again from the book, you can email me, or we can have a doubt session, especially to address all the doubts from 1D and 2D. So this PML was a very important topic. And another important topic that we'll do now is the total field and scattered field formulation. So this is something very close to what you might use in your in solving a problem. So sometimes what happens is we like one important thing is that we usually are working with plane waves, and we might want to find out S parameters. So for these two things, what is called as total and scattered field formulation. So the concept is very simple. Is that you have this particular simulation space, and you want to know what happens if there was some object over here, and if a plane wave was in like incident on this object, and obviously this object will then scatter the wave, and you wanted to know like what like how this the you wanted to observe how the this particular object is scattering this the incident plane wave. And for this we what we do is we divide the simulation space into one region known as the total field, and outside this total field is this region called scattered field. And then again we have this gray region as the PML region. So and for this what we do is we introduce a plane wave over here. This plane wave travels in this direction. So introducing a plane wave is also is what we'll see now. And so this plane wave is introduced over here, and what this plane wave travels in this direction, it hits this particular object. And what and when this wave reaches, and when this incident wave reaches these boundaries, is we subtract them such that we only have the scattered field coming out of this particular box. And so we will be easily able to see how the wave is being scattered by this particular object. So this is like these are like, for your reference, that we are often interested in plane waves, and plane waves are used for calculation of radar cross section. Similarly, for Am I still audible? I think I lost you guys for some time.
Yeah,
I'm audible?
yeah, Anand.
Oh, okay. So yeah. So yes. So plane waves are basically used in calculation of RCS and even for like the wave radiated by most antennas in the far field are again considered plane wave. So for this particular total field and scattered field formulation is what we do. Now to introduce to make this particular region as total field and this particular region as scattered field, what we do is we introduce an incident array. So this incident array is basically this is not essentially, hence we call it auxiliary, because you can again see total and scattered field without using this technique, but you'll have to do what we do is we have to after the simulation you might have to like subtract the scattered field from the incident field. So instead of doing that, we introduce this particular auxiliary array where this incident array will contain a plane wave propagating in this direction, and this incident array travels through this space, interacts with this particular any this object or any and all object inside this region, and once this incident array reaches this particular boundary, you subtract it from the total field. So so all you will be left with it will be will the scattered field in this region. So what we are doing is we are keeping the incident wave separate from the total field, and inside this region only they both will be seen together, will be added, uh, and outside this they will be the incident field will be subtracted from the total field such that you just see the scattered field over here. So this is basically the concept behind the total field and scattered field. uh, and after this uh, we'll address the issues that will arise, and how the update expressions will be modified. So okay, I'll stop over here and take questions if you have any before we start with what will the issues happening at these boundaries. I hope everybody followed the concept of having total field and scattered field, and the logic that we are keeping an array which is having the incident field added to the field calculation over here such that we achieve total field, and outside this we will remove the incident field such that what will be left will be only with the scattered field.
Anand, I think everything is fine, but suppose we make an array after a scattered field. So it's fine that anything, if you calculated after the between a scattered field and a PML region, is must be a reflected. Is it?
Yes, yes, not just
Suppose
reflected, scattered basically.
scattered.
What scattered? Yes,
And if we need to calculate after a scattered field a reflected thing, so how we can
I could
suppose
not follow your question.
in a
Okay.
total field region, we need to
Yes.
calculate a scattered.
uh, the scattered field will be included in the total field region, because the update expressions over here will be calculated based on the interaction of the plane wave with the object. So whatever we will achieve will be the total field only, and outside this is what we do is we subtract the incident field in this incident array. So what we are left is the scattered only.
Okay.
So in this region, the update expressions will calculate the total field, because we will update them with the incident array. So the incident array will always contain the incident field. This total the E expressions and the D expressions inside the E, D, H all will have the total field expressions over here. We will have an E incident Okay, so I'll just write this over here. So we have an E incident which will keep the incident array. Inside this region, we will have we have the E, D, and HX and HY. Okay, yeah. So this EZ, DZ, HX, and HY. All these things inside this region will calculate the total field, and outside this region, the same this particular the same things will be what we'll do is we subtract from this. We will subtract this E incident, and similar for each E incident, we will also have H incident as well. So we'll subtract the H incident from the HX and HY, and E incident from the EZ, so that we will achieve the will so that we achieve the scattered field, and they will also be stored in the EZ and DZ only, and will be using this EZ for plotting this entire space. But yeah, so outside this region is what we are doing is we're subtracting the incident field, and inside this region, this the we are calling it total field because it will have the incident field in included in this, while the update equation works in that way. Like, were you able to follow any follow up questions on this thing?
No, I don't think so.
Okay, so yeah, so first we are like this, how do we include a plane wave? So so you'll find this funny. What we are doing is we are introducing a 1D array over here. So this E incident is actually a 1D array, and this 1D array works in such a way that it to like cross section. Yeah, so if we just considered this particular line of node, and we introduced one Gaussian pulse over here, and this particular Gaussian pulse was added to each E field over each source, like for the entire line. If we added Gaussian pulse at each of these nodes, what will happen is you will see a series of Gaussian pulses. Okay, so try to imagine this in 3D. So this will actually appear to be a plane wave. If at each node you added the Gaussian pulse, so this entire Gaussian pulse will again become like a plane wave traveling with the constant like, yeah. Do you guys follow like what I'm trying to convey over here? That at each point, instead of adding a source at just one point, we are adding the source at the entire in the entire row. So the entire row will be updated with a Gaussian pulse, as which will effectively become one plane wave.
Yeah, yeah.
Okay. So to introduce a plane wave, what we do is instead of adding a point source, we are adding a line source, and the line source is updated with a Gaussian pulse. So a point source with a Gaussian pulse will travel in the circular fashion around, and if it was a line source, the Gaussian pulse will travel like a plane wave in one direction. And and what we are doing is we are keeping we are introducing for simplicity, what we do is we are introducing this auxiliary incident array as 1D. So for the E incident, it will be just added in one at one location, and this E incident will be updated to at all these points. So we'll see this in the coming slides. Now, like, what is the issue with the TSSF formulation at the boundaries? So so this JA and IA are the position which defines where the TFSF boundaries are. So at this particular, you can see that, okay, so this. boundary is basically dividing the total field and scattered field. Now, if while calculating the this electric field or this current density, so the electric flux the, over here, or the magnetic fields over here, what is happening is that these nodes these nodes take the need the values of this field as well. So, but what happens is this is a node lying in the total field region, and it is being updated using a field value from the scattered field region. But this will cause issue because this the electric the H field over here is not consistent with the H field over here, and to solve and this is and to solve this issue we'll have to do modifications. Similarly, if you look at the magnetic field being calculated at the this this node, this requires the electric field over here and electric field over here. But this node lies inside the total field, which won't be considered consistent with the electric field over here. And so we need to make accommodations. We need to make changes such that then the value of the magnetic field being calculated over here is correct. So this issue arises for the nodes lying near the boundaries, and to for these we make changes. So basically, three places must be modified, and these will correspond to dz, hx, and hy for the values which are lying at the field. So let's take this example. So for j equal to ja, so if we take this particular node, okay, so this particular node is being updated by this magnetic field and this magnetic field, but this magnetic field is not total field. So so this is just scattered field, and we can represent total field as a sum of scattered field plus incident. So what we do is for the magnetic field value over here, we compensate it, and we add the incident field value. So we are keeping the incident field for hx in hinc. We are keeping the incident field value for hy in hinc, and we are keeping the electric field value for uh, the incident electric field value in EZINC. So we are updating these values separately, and we'll use these values to compensate over here. So we need to calculate the electric this flux density electric flux over here, and we have this SF plus INC already happening over here. So what we do is we just to compensate it, we add the magnetic field, the remaining value which was missing over here. Similarly, we do this at the same thing at GB, which will be at the other boundary over here. So this has to be done similarly for while calculating the hx. We hx equal to ja. Okay, so for ja we are trying to calculate hx. So hx over. Okay, so while calculating this particular uh, while updating this hx value over here. So for this, we need this node and this node. So this node is actually in scattered field. This node is also in scattered field, but this node is in scattered field plus incident value. So what we do is while calculating the updating this, we compensate the incident value over here. So what we do is we add the this is at here hx. Okay, so yeah, so we compensate it by introducing this term. So why are we adding this over here? Okay, so what we are doing is that we the this hx was updated using the scattered field expressions, and what was missing was the incident field value over here. So we are adding the ez incident field value, which was supposed to be here, to this hx value. And similarly we do the same for the hy as well. So I'll stop over here and take questions. I think this was a bit confusing, so I'll let you read the slide and take any questions that you have.
I think it's okay. Able to understand.
Come again, Ankit. I could not follow you.
It's okay.
Okay.
Everything is very clear.
Okay. So we'll wait for others. Maybe if anybody else has doubts, because this is very important. Like how we are doing modifications near the boundary. Yeah, just to make clear, I'll just highlight the boundary so that you can see. Should have made this figure in color. So the boundary is over here. Okay, so I'll just go over this once again, and then we'll move to the coding part. So essentially, what we have is this, in the total field region, can be expressed in terms of scattered field plus the incident field, and any node that is being updated near the boundary will be updated according to either the total field or the scattered field update expression. And what happens is, at the boundaries, for example, this particular node has been updated using these two nodes, and this node was updated using the scattered field uh, uh, values. So this will have this incident field value missing. So what we do is we include this incident field value. Similarly, if while updating this particular node, this particular node was updated using the values for total field for over here and over here, and so this particular part missed the incident field value. So similarly, we included the this term over here, so to compensate for the incident field value missing in this update for this particular node. And this is how we are modifying the update expression for the nodes at just the boundaries. So all the nodes at I equal to a and j equal to a, and similarly jb and this ib will be modified. So I hope this was clear. And using this, so we will obtain the once we have modified the nodes, we will obtain these results. So a plane wave was generated at this boundary. Okay, no, I did not put the pointer. So a plane wave was generated at this boundary, and since there are no objects inside, this particular incident field will stays inside this total field only. Since there was nothing, there was no scattering, because there is no object inside. So in the coming slides, we will see result when we have a cylinder over here, and there we have some scattering. Similarly, if you see that in 3D, okay. So a plane wave is generated. This is what I was talking about. So a plane wave is generated. It travels inside the total field only. So we are not able to see the plane wave outside the total field, because this is the total field has the incident and scattered both, and the outside is just the scattered field. So if there was any object over here, the scattered anything that was scattered would have been visible in this region. Okay, we'll come back to the code. I hope I have result. Okay, so uh, yeah. So this particular result is when we have a dielectric cylinder over here. So the incident field just remains inside this region, and outside the total field boundary, whatever you observe is the scattered field. Similarly, you will be able to see. So this incident field, it so there is a dielectric cylinder over here, and yeah, so you can see this. This was the incident field, and this is not visible outside, and outside only the scattered fields are visible. So if there was some object inside, you will be able to see the scattered field in this region. So this is what we are aiming to. Until now, we have seen how to introduce a plane wave. So over here, we just saw. Okay, so over here we had seen the plane wave being generated, and it traveled in the total field region, and no scattered field was here. And for this, so we'll look at the code. So our first aim is that uh, we have a region where we have this we need to have a total field region, a scattered field region, and again PML is also required. So and we have a PML region. So for this, we are already familiar with these parts, that we need to define the problem space. We we define IA, J, and IB and JB for the total field, scattered field boundaries. So since we already know that if this particular region has 100 nodes, the PML will have 10 nodes, and we are keeping the 5 nodes between the total field and the PML. So the scattered field has 5 nodes over here. So I've kept this as 15 and use the same values for the other boundaries. We define the number of steps, the time step. This whole thing is already known to us. We initialize the region for free space. Uh, Now, what happened? What we discussed, that the E incident and this E incident and the HX incident, all um, these are 1D, like one-dimensional arrays. So for them, we won't actually use PML. We will just stick to the old ABZ. So we have defined the EZ and HX incident. We have defined these temporary values for the ABCs needed for this 1D incident. These things are already discussed for PML. Again, this is again for PML. This is for PML, the X direction PML, Y direction PML, defining a source, and we'll start with the main part of the code. So when starting with the main part of the code, so here are the major changes that we are doing. So we are including this EZ update expression. So EZ, the incident field is updated in the same way that we did in the 1D update. So EZ is updated on the basis of uh, HX for 1D case. Now, for this EZ, when the since this is 1D, although the problem space is 2D, and but this the incident field just travels in one direction, which is used to update all these regions. But we will since this is 1D, we will need the absorbing boundary conditions for this EZ field. So for that, we are using the old ABC that we see in the 1D case. Now this the DX field is updated using the same update expression that we use for 2D FDTD, and we are including the source over here. Now again, the change that happened was over here. So we are at the boundaries. What we are doing is we are adding and subtracting the incident field. So as soon as the incident the for example, we are introducing a source over here, and as soon as the source enters the total field region, we add the incident field to the DZ, and as soon as it exits the total field region, we subtract it. And this is in accordance according to the total field scattered field formulation, the three regions that we needed to modify the nodes according to which. So following those issues that we are introducing this set on this update equation. So we add the incident field to the dz value over here and subtract it over here, and we do it according to the this J and JB part over here. So this is JA and this is JB. So and also we need to make sure that the nodes over here are updated properly. So that is how we are doing it. So I'll stop here and take question before we move to the next slide, where we see the other changes that we have done for the total field and scattered field.
Anand, how you choose this EZ incident fee is equal to pulse?
Okay. Yeah. So we have like just we discussed that this EZ is our 1D. This is a one dimensional array. So that is why we just have one coefficient over here, and so I've just written 3 over here. You can also like so this 3 is the node at which we are introducing the incident field. So and this pulse over here is basically adding a Gaussian source. So for EZ, what will happen is we will see this, but only a Gaussian pulse. But when this particular EZ is used to this EZ, so we know that in FDTD all the update expressions are interlaced, right? So this EZ is being used to calculate. Okay, so in the next slide, will see that this EZ is used to calculate the the HX. So HX is updated from this EZ, and this HX, this HX incident is updated using EZ, and this EZ, this HX, which is updated from EZ, is used to update this DZ. So this DZ will finally be updated with this 1D Gaussian, which will translate over here to a line source.
Yeah.
Were you able to follow, or I can repeat this?
I understand.
Okay. Okay. So essentially, yeah. So oh, the very this fascinating thing about RTD is that once E is calculated, it is used to update H, which is used to update D, which is used to again update E, and which is again used to update H. So the cycle goes on, right? So this is what happening and what is happening, and at any step when you introduce a change, this will again propagate inside it. So yeah, so we are updating the ez value, ez incident value, which updates the hz incident value, which updates the regular dz value, and which updates the regular again ez value, which updates the regular hx and hy value, and then this is used to update these values over here. And in between, we are just since the TFSF formulation is included in the middle. In between, we are just modifying the HX and HY and this DZ such that they follow the TF SF formulation. Okay, so I'll pause again over here so that although I've scribbled a lot, maybe you are able to see the code, and you have any questions, we'll take. Okay, so we'll move to the next slide. A general question: is there any specific reason to put ABC in between E and H loops and define E first and H second? Uh, so although I've never tried it, but I don't think it will affect much. But okay, so yeah, ABC is put in between E and H. Yeah, so we follow this, and because if we update E just after like if we update H just after E, you might miss the update like the absorbing boundary thing. Okay, it will be a good exercise if you try to change it. I won't comment right now because I have not seen this. So this will be part of your assignment 3. Change the order of H, E, and ABC, and we'll see what happens. So I won't comment anything over here since I have not tried it, but this might affect. Okay, yeah, thanks for the question. Good question. Okay, moving to the so we have already seen in the previous slide till here. So till now we calculated we updated the incident value. We added a source and we updated the dz value, and then again updated the dz value using this TFSF formulation. Now what we do is this is a regular expression that we have seen in the 2D PML. So we are updating the EX from DZ. Now again we are so this is a new syntax included. So we are updating the HX incident from EZ values. Then again, so this is from the so this is not new. This is calculating the HX field. This is new. So this is new. This is new. So over here, what we're doing. So we have seen we needed to make changes at 3 positions. So one was over here. So one change. The first position where we made changes was over here. The second position where we're making the changes for TFSF is over here. So we recall that we have this total field region, scattered field region. And for the scattered field region, what we are doing is we have added the at one place we will add the incident field, and at the second place we will subtract the incident field. So that is what we are doing for the hx field over here. Now after that, this is old, so this is say updating the hy field. And okay, so the second position where we are making the changes, and this is the and updating the hy field, and then again we are making the changes, the third place where we have to make the change for tfsf. So similarly for the hy field also, we in the region, this is we will add the incident field, and over here we'll subtract the incident field. So these are the three places where we made changes, and we introduced the e incident and h incident, and for both of them we had update equations. So a total of 5 new loops added, 3 of them adding and subtracting the incident fields at the boundaries, and two loops to update the incident uh, e and h fields. This remains same for on the plot window, and we then this closing the video writer file. So this was all that we needed for these two. So this, using this, you will get this particular code. So the E field is added over here, and this propagates in the total field region and gets subtracted over here. And to plot this window, I've used ImageSC, and this is again using surf. So I've like when I share, you will be able, since for scattered field, sometimes it is easier to see in the like this type of plot, that cross section type plot. So I've added this window over here. So any questions till now? So we'll take any questions you have. Otherwise, we'll move to including a dielectric cylinder in the simulation space, in the problem space. Okay. So this TFSA formulation is only useful when you have a dielectric object in the problem space, so that this plane wave is at least incident on something, so that you will be able to see some scattering. So to do that, we need to include this a dielectric object inside. You could also include any like for to include any object, it is fairly simple. We could have just used square or cube, like included a square object over here, which could have been a cube or cuboid, since we are looking at the 2D uh, like cross section over here. So, but sometimes this is so I've shared this code for adding a cylinder over here, because so like scattering from cylinder will be like, this will be more useful maybe in for your research or project. So adding a cube, it would have been fairly simple, that you know the length and breadth, what you do is you just modify the GA and GB, which are basically keeping track of these permittivity and conductivity region. But for including a cylinder, what you will have to do is you'll have to modify this GA and GB such that they are in according to the object. So you can add any number of object. So all you need to do is just modify these variables which keep track of the permittivity distribution in the space. So this particular space has this particular space of and you have this total field region, the scattered field region, and PML region. So GA and GB and all the other way this GA is essentially keep tracks of the permittivity, and it is usually one for free space. So as soon as you introduce some value to it, it will essentially mean that there is some object inside somewhere. And for TFSA formulation, or what you need to do is your object should be inside the total field, so that the plane wave starting from the boundary of the total field will be incident on this object. And what the scattering will be like you can observe the scattering in the scattering region over here. So this is fairly simple code that you'll have to include in the previous code that we just saw. You take a radius, and for example, you want a 10 centimeter wide cylinder. So you take so this is in meters. So you take so this will be 1.1 meter. We divide it by the number by the cell size DDX. So you this will give you the number of nodes the cell this the number of nodes that this radius should have. You define the epsilon and sigma for the cylinder, the center of the cylinder. And now what you do is you run through these loops. You start with the from J and go till JB. So essentially what you're doing is you're scanning through the so your JA and JB are over here, right? So J and JB are over here, and IA and IB are over here. So what you're doing is you're scanning from this region till here and this region till here, and at every node that you inspect, so if you take a node over here, you inspect whether this particular node is inside the cylinder or not. You calc so this x distance and y distance and this distance. So what you do is you're calculating the distance from the center. Uh, distance. Your center of the cylinder is over here. You're calculating this distance and dist over here. So and you check whether this distance is less than the radius. So if this is less than the radius, what you do is you assign that particular node uh, this epsilon and this sigma. Otherwise, you skip this. So since this node is outside, this if won't be executed. So and if this node was suppose over here, so this distance will be this distance will be less than the radius. So this condition will be true. And what you do is you modify the GA and GB this coefficient such that this includes this epsilon and this sigma values. Pretty straightforward. This if this was just a square, what you would have done is you would have started this for from J. There would be a for from I, and you would just directly assign GA equal to and you would know the positions, right? So if you would know from the start position, you would know the end position. Similarly, you would know the start position in the J direction, the end position in the J direction, and you will just assign these two things over here. You will assign GA and GB, and you will end the loop. So this is how you include a dielectric cylinder in the 2D space. So I'll pause over here and take questions. So this is mostly like this is all coding and very less electromagnetics. I'll pause and take questions if you have any doubts regarding this code.
I think it's okay. The, it should be like a staircase approximation because at the end of the day we are working in a rectangular section, no?
Yes.
G
So
and
yeah. So over here, what happens is if you look at, for example, if this was the one of the edges of a cylinder, so what will happen is you will have some nodes going on like this, right? So yeah. So when what you're doing is while calculating, you're selecting this you're selecting this node and checking whether this node is inside the radius. And similarly, this node, fortunately, this node lies on the point, this node lies on the point, but this node, this node lies outside, and this node lies inside. So what will happen is you will end up having a staircase approximation. So this node will lie over here. So the cylinder will be defined like this. So in this region, it is not taking accounting for the permittivity for this particular part. So yeah, this is staircase approximation. So and in the next slide we will see how how to approximate better for smoothing of this. That is all we'll discuss the next slide. Okay, I guess this was clear,
yeah, yeah,
and so we have already seen these results, and maybe you can see this once again. So there's a dielectric cylinder somewhere over here, and the incident wave again interacts like this, and say the total field boundary was some till here. So anything that you're seeing in this region, and this region is all scattered field. So in the previous slide that we saw that for including a the electric cylinder. So that's over there we as Ankit pointed out that we were doing staircase approximation. So at the boundaries, the cell would be the unit cells would be approximated in this fashion. So, so this might happen that you are approximating. So, uh, and so this will again include some errors. And the better you approximate, the more better results you will get. So one way is that one way to better approximate is you change the cell size. But again, if you discretize the entire space with a smaller cell, it the computational burden will increase rapidly if you do that. So instead of that, what you can do is use the approximation technique on the borders, on just the interface of the cylinder. And one of the ways is to use an approximation technique where you fill in the cell with a weighted value of the permittivity. So, for example, if this was your cell, and what you do is, for example, and this is the cell lying over here. So, in this cell, what we can do is we can divide this cell into further smaller parts, and in these smaller parts, we can check whether this particular part is lying. Uh, is lying inside the region or outside the region. For example, since this part if is passing through over here, and if this accounts for the whether if this part is inside the cylinder, so what we do is we add a weighted value of the epsilon in this in the code. And similarly, we check for this part, so this will again add a weighted value, and again for this part as well. For similarly, what we do is we check this, and this will again add a weighted value. This will again add a weighted value. So what we do is instead of taking this whole cell at a time, we take the weighted values. So for example, this if this cell was supposed to provide epsilon, each cell will supposedly provide epsilon by 9. So we run through the loop. We check whether for each nodes, and we see. So 1, 2, 3, 4, and 5. So 5 cells are inside this cylinder, and 4 cells are outside the cylinder. So this particular cell will effectively provide 5 by 9 epsilon. So instead of using epsilon, either epsilon or 1, that which is free space, we are approximating at the boundaries according to how much this cell is filled with the dielectric. So for example, if a cell was filled very less with the dielectric, so this could be either this could be epsilon by 9, and if a cell was filled almost, then this could even evaluate to 8 epsilon by 9, which is a very good approximation uh, technique over here. So this particular code is how we do this. So we start calculating the distance, and then again inside this we open another loop uh, where we check whether the so we are actually dividing the each cell into 9 nodes, calculating the distance. And if again, so that we discussed over here, if that particular node is inside the cylinder, we add a weighted value. For example, since we are dividing this cell into 9 parts, so we each part will contribute 1 by 9 values. And initially the entire space is, since it is initialized with free space, so this entire space is already initialized with epsilon equal to 1. What we do is we subtract this 1 and add this epsilon r, which is supposed to be 30, and then divided by 9. And this is added to the epsilon value for that unit cell. So for this unit cell, this could earlier this could have been either 1 or 30. Now what we do is we divide it into different cells and add the value. So that this value can now range between 1 to 30 based upon how much the cell is filled. So this is the code. You can go through this code and have any doubts, you can reach out to me. We can discuss in the next class. So yeah, so these are the results. So if you are using the staircase approximation, which is either in or out technique, you will have a cylinder looking like this. So I've plotted GB over here. So this is how GB looks. And if you use a smoothing technique, so you can see that at the edges, some cells are filled. So inside they are all 30, outside they are all 1, and over here they are filled with some values which are in between 30 and 1. So looks pretty smooth on the borders. So smooth technique. So what we have done is we have smoothened the boundaries. So this is all that we will cover today. So I am not I've already shown the code for the TFSF thing, and given the snippets for the snippets for this, and this case has been given. So that will be a part of your assignment to include the snippet and see the results. I've already shown you how that a plane wave interacting with a cylinder looks like. So we had one more question, right? what happens if E, H, and A, B, C are changed in order. Okay, so this question Priyank asked, and I think this should be an assignment for everyone. So at the end of this class, I will share the TFSF MATLAB code. The first thing that you have to do is inspect each line, and any doubts that you have we can discuss in the next class. You have to modify the code to include a dielectric cylinder in the problem space, and the relative permittivity, conductivity, and radius are given. So the snippet has already been shown in the class. So you can refer to the slides and include the snippet. Uh, so all, the snippet will be basically included just above the. This will be included above outside the main loop. So before you start with the main part, before the main part, you can just include the snippet, and that will do. Make sure you have already initialized GA and GB with 1 and 0. After that, you can include this particular snippet. Then you should try to vary the values of permittivity, conductivity, and radius, and see how uh, the code works. And the last thing was that include the smooth transition. So again, this snippet has also been given. So all you need to do is replace this snippet which you have added over here with this particular thing. Yeah, this is as assignment 3. I'll take any questions that from so now so this is all that we had to cover today. I'll take any questions that you have from the assignment or whatever that was discussed in today's class or previous classes. So if nobody has any questions, then okay. So this is all that we covered. We have covered. So we have done PML, shared the MATLAB code. If you have any doubts, please reach out. So I've shared this thing. Uh, Everything is available on the ISSS portal, and I'm also sharing the website to my link, the link to my website where I'm uploading the file simultaneously. Today we covered these two topics. Again, very important topics, especially if you're trying to implement something. And in the next class, we'll look at introduction to 3D FDTD and take any questions till now we what we have discussed. And based upon the next class, we'll decide whether we have the next class will be the last class or we'll have two more classes. Yeah.
Anand,
So
Anand,
yes, Ankit.
uh, we've seen the application of TFSF would be calculating RCS cross section or maybe some S parameters. We haven't done that
Yes.
any practical application that we use in microwave. Suppose there is a
Okay.
dielectric slab and you are
Okay.
obtaining TFSF and in a plane wave imping on that dielectric slab, and then we need to calculate the reflection coefficient and transmission coefficient so that we can analyze the frequency response of that dielectric slab or particular frequency.
Okay. So in so doing that like following one of like one of this projects like thing will be too much for this course. So So that so everything that is needed to like as you said, so there is a space where we have a dielectrics slab or a cylinder, and a plane wave is incident, and then we are trying to measure the scattered field or reflection coefficient. So everything needed for this implementation has already been covered in the course. So we have already seen how to do Fourier transforms. We have already seen how to collect the scattered field, and we have already seen how to store the how to store the scattered field and incident field. Like we covered that today. We already know how to do Fourier transform. So all you need to do is pick a point where you want to see the field, store that store the values of that point, the field passing through it in one of the vectors, perform Fourier transform, and then you will be able to see the frequency domain plots. And to get the reflection coefficients, all you need to do is the whatever you have received, the received field divided by the incident field, I believe, is the reflection coefficient, like something like this. So whatever you so yeah, so everything that is needed to what the thing that you asked is has already been covered in the class. So you can try. If you feel any difficulty, you can reach out to me. So
Okay,
yeah, so
okay.
everything that was needed was has been covered already. And regarding microwave devices where you need to where you are involved with I and V, so for this I think I will recommend you to go through the book by David B. Davidson. David B. Davidson. It is one of the textbooks I've used for my course as well. So using in this book, you will be able to see one thing which we have not covered in this particular course was FDTD for 1D FDTD for transmission lines. Uh, but we have covered enough thing. We have done 2D, so this thing will look like nothing. So we have already done 2D. So going back to 1D and looking at the I and V expressions, so won't be difficult. So over here, what instead of using Maxwell's equations, we are using the telegrapher's equations. So the update equations are calculated from the telegrapher's equations. And you're familiar. And all this thing is based on that we have wave equations. So Maxwell's equations also, when you solve, you will get wave equations. Telegrapher's equations also, when you solve, you will get wave equation. So the just the variables will appear different, but everything rest will remain same. So yeah. So for if you want to do it based on devices which involve current and voltage, refer to this textbook. Otherwise, we have covered everything needed for dielectrics and E and whatever problems require E and H.
Yeah, I think so. Cover all the things, especially on the uh, frequency domain transformation. You already seen how to find transmission.
I lost you for a second. Come again, Ankit.
I think you already cover all the basics. I just
Yeah.
waiting for. Is there some other classes also for this application, or it's fine?
So this lecture was supposed to supposed for students and everyone who wants to get started with FDTD. So the advanced applications, I won't be covering them, and mostly uh, the lecture was the course was designed for basics only. Uh, so we'll end with discussion on 3D. We'll see whether how much we can cover. So I'm planning to take 1 or 2 lectures at max, and we'll end this course. And maybe in future I can offer an advanced course based on FDTD only. But yeah, so in this course, so 2D is all done. So no more problems based on 2D, and we'll see how much we can do in 3D.
Yeah, fine. I'm really glad to see you explaining very small concepts.
Yeah, thanks. So in this, all the things which I've tried to cover were based on my own experience of how I have used the tool, and like everything which I felt necessary that should be addressed, especially from the point of view of implementing using FDTD. Like this course was mostly focused on how to implement, how to write the code, and if you want to get more in-depth knowledge on FDTD, I would recommend you go through a course on NPTEL by Uday sir. You Uday Khonkhose, Khonkhoj. I some so okay, this spelling might be mistake. But if you search for Uday Khonkhose on NPTEL, you will find a very good lecture series on computational electromagnetics. So Uday sir has covered almost all important methods including FDTD, FEM, and other techniques, MOM. So yeah, so very good lecture. Please take time to go through this. You will have very good understanding of all the methods, including FDTD.
Yeah.
Yeah. So if nobody has any questions, maybe we can end for today's class. Yes, Ankit, you were saying something.
No, nothing.
Oh, okay.
Everything is fine.
Yeah, I thought you have any questions. Yeah, okay. So I guess that was all. If so, please try to do this assignment. Yeah, and by the after the next class, I will share the this modified codes as well. But I will give you time to do it yourself. So see you guys again next weekend.